All right, good morning, everyone. Welcome to this talk, The End of the Data Ice Age. My name is Hugh McKee. I'm a developer advocate at Lightbend. I'm delighted to be here. This is one of my favorite cities to be back into, but I'm also delighted just to be at a conference again. After a couple years of doing virtual conferences and not being able to see you guys, I still can't see you because of the lights. The lights are blinding me, but I know you're out there, so it's great. So in this talk, the inspiration for this talk was something I've been working on over the last few months that got me kind of rethinking about how I program, how I use technologies, how we as developers use technologies, and just kind of challenging things because and you'll see what I'm talking about. I'm going to give you examples of what I've been working on. But it got me thinking about this whole thing of compute, what I'm calling compute and persistence. So I made this picture. A lot of the visuals in this presentation I do with Blender. If you know Blender, it's this great open source 3D tool, and you can do some amazing things with it. So doing a picture like this is kind of cool. It's all 3D and everything, but it helps me get some points across visually. So at this picture, I'm trying to show there's a layer of hardware and there's a layer of persistence. The hardware is, this kind of looks like a circuit board, and the persistence is these little kind of glowing towers of data. And the question that kind of came in my mind was, we're in the third decade of the 21st century, and we're still doing computing as far as how we handle computing and how we handle data fundamentally in the same way that we have been for decades, many, many, many decades. I'm old. I've been doing this for a long time. I love writing code, and I just don't want to stop until they kick me out. But I've watched things evolve and technologies advance over a long period of time. But it's like I'm sitting here, and like I said, wait a minute. Again, the third decade in the 21st century is like, why is the hardware still influencing the way I write software so much? And so that was kind of the inspiration for this talk, because I'm working on something now where it's at a higher level of abstraction. And again, this is another Blender image. If there's thousands of tutorials on Blender and YouTube. And if you have any question, like, how do you do something, you just go there and you find it. And I came across somebody doing a tutorial with this kind of picture, and as soon as I saw it, I said, this is what I see in my mind's eye when I'm thinking about this level of abstraction, where these little spheres are units of data. And these units of data are interconnected with each other, and there's kind of flows that are going on between all these spheres. And this is this new abstraction layer that I've been playing with, and the picture that was forming in my mind. So this is what I want to show you. Hopefully at the end of this talk, this picture will make more sense as far as what I'm talking about. But it really led me to this whole idea of, could this be the end of the data ice age? Question mark, it's the question. So to start things out, for a long time, even before we knew what we're calling it now as stateless, we've been building stateless applications, and there's great tools for doing it. We know how to do it really well. It's been institutionalized and refined and so on and for decades. And the approach is great, dealing with the current state of technology, because it's dealing with the fact that we do have these two fundamental layers. We have a compute layer on the top and a persistence layer on the bottom. So the compute layer on the top is stateless. And one of the great things about it is if we want to scale, we can just add more instances. Now, the databases have to scale in a completely different way, but at least in the application layer, we could scale. But things get interesting when we're dealing with data, because say, there's a request comes in to one of the instances of the stateless app to retrieve some data from a database, so it gets a copy of it, and it pulls it up into memory and into the compute space so that it can act on it. And then say another request comes in for another piece of data, another state change that wants to occur. So that request comes into the instance on the left. But while that instance has that copy of the data, another request comes into the middle instance for that same unit of data. So now there's a copy of that same unit of data in two places in the stateless layer. So the first instance, does this work, makes a state change, and persists that state change down into the database layer, the persistence layer. And when the second instance tries to make a change and persist it, it's protected because it's built in. There's like some form of optimistic locking or something like that, so we're not going to overwrite a previous update. And again, we know how to handle this, but it's like we have to know how to handle this. And it's like, why do we have to know how to handle this is kind of the question. So this is the common platform, these two layers. And again, the database is there, I think, if you look at it from that perspective of we got this persistence layer. And databases are also decades old. There's great computer science in them. They're very powerful in themselves, but they're there, and they're a big attention for us. We spend a lot of time understanding how to use them, and you really exercising a lot of intellectual capacity dealing with them. But here's another way to think about it: is that there's data, there's information, and it's kind of in a hot state and a cold state. And this is why, I thought about the Ice Age, where when the data is down in the database, it's kind of frozen, right? If you want to change it, you got to bring it up into some kind of hot state layer so that you can compute on it, make state changes, and put it back down into the cold state layer. And this is the inspiration for the thinking about the Ice Age. So that's just kind of a quick review of the compute and persistence perspective of things and how hardware technologies have been influencing that for a long time. But let's start looking at this abstraction layer that I'm talking about, this pretty little picture that I've got here. So the concept starts with, think of state as an entity, which we do. And so this entity has some kind of API, a defined way of sending in commands or requests to do some form of manipulation. And think of this state as having code and state. So one way to think about this is this is an object. It's a stateful, durable object. And this is the fundamental behavior of it. So commands come in to an instance of this state. So say the state represents a shopping cart, for example. So if there's hundreds or thousands of people right now shopping on your app, there's hundreds or thousands of these stateful, durable object instances in the compute space right now, each one handling the state changes of individual shopping carts. But it is, think of it as an object. So commands come in, the code executes, it makes state changes, and the state changes are sent out to some kind of a state store for persistence. But let me show you some code where this is handled. So this is I'll tell you what this code is at the end, but let me just show you a little bit of what's happening in this code. So it's just that, this is Java. It's derived from some basic abstract class that's called order item. And it's got an API. There's some, the base class has some methods like create order item and shipped order item. And this method takes in two parameters. It takes in the command, the request to perform, like this create operation. But the other thing that's being passed in is the state. So what's happening here is that there's an underlying abstraction layer that this object, this durable stateful entity object is running in, where the code here isn't involved in the retrieval of the state. It's like a traditional operation. We'd get some kind of request come in, like a command. We do a retrieval of data from the database because it's a stateless system, so we have to get the state right now. We make our change, and then we send the state back out. Here, the state's injected along with the command. So how that state's retrieved, how that state's managed, where it's stored, connections to the database, all those things are abstracted away here. Now, we have to implement this method. So what I did was I implement this handle method. And this is just my own style. You can write it any way you want. But one thing that you have to do is there's a inherited method in this class called update state. So it's a, effects.update state. So I wrote a little update state method that takes in the command, takes in the state, and returns the new state. So this is where the altered state is returned back to the abstraction layer. Now, what happens to that, where it goes, where it's stored, how it's stored, all those things are being handled by the abstraction layer. So the concept of the database is almost gone here, because this is where it got me. When I was writing this kind of code, it's like all of a sudden, I'm spending all my time thinking about the business logic and the functionality of this system. And and the same pattern with another command, this shipped ordered command. It's passed in the state again, and I perform some kind of update state to alter the state based on that particular command, and I return the altered state back to the abstraction layer, and that's it. It gets even more interesting, though. This is the same flow, but now it's event sourcing. So instead of admitting the total altered state, what this entity is set up to do is it commands come in, you perform the command, but instead of admitting the complete altered state, you're admitting events. So like you add an item to the shopping cart, you admit an item added. You change the item quantity, you admit an item changed. You do a checkout, you admit a checkout event, those types of things. So this one I think is really cool because it makes event sourcing like super simple, because again, all you're thinking about is commands coming into this and what do I do? So let me show you an example of this. So in this demo, there's a shopping cart, very much like the other one, which is more, the first one I showed you is more like a CRUD-like type of, create, read, update, delete type of, it's called a key value or value entity. This is called an event source entity. But it's the same kind of thing, like add item, this method add item, the state of the shopping cart is passed in from the abstraction layer along with the command. By the way, I mentioned that there's thousands or hundreds or thousands of instances of these entities hot in memory. Routing commands to a given specific entity object is handled also by the abstraction layer. So here, it's a little bit more, but again, this is my style, not something that's dictated by this SDK that I'm using. So this style, I just have a validation step. So I do a reject, which returns a Java optional, and if it's not rejected, then I'm going to do a handle. So the reject method, it's just checking out things like if you can't add an item if the shopping cart's already checked out, that type of stuff, right? And if it's, it's not right, then it's just going to return an error and it won't handle the request. But in the handle method, here, the difference is instead of doing a update state, it's emitting an event. So right in this line here, it's emitting an event. And I just wrote this event for method myself. And just again, how you do this is up to you, but this is just my code in here. So this event for method is just, let me show you it. It's just creating the event object. These events are all kind of code generated from a definition. I don't have time really to go into that level of detail here, but we're just kind of building an object and loading it up, setting it up, and it's just using a factory pattern to do that. That's all. So here it's emitting an event. Now the other thing that's happening though is that if I go back up to the commands, sorry for scrolling here, you can see there's these methods that have to be implemented for processing commands. You can see there's like 3 of them. There's 3 of them at the top. But then there's another series of methods that have to be implemented for handling the events. So what happens is that when that emit event occurs and we give it back to the abstraction layer persists that event in some kind of an event store. And then once that event has been safely persisted, then it invokes these event methods. So if I show you, let me show you one of these event methods. What this is doing is you can see the method's returning the altered state. So what's happening here is the state change hasn't occurred yet. The event's safe, so now let's just alter the state, meaning, like if it's add an item, let's add the item to the shopping cart object, and then this method then returns that altered state back to the abstraction layer. So there's kind of a two-step process when you're using event sourcing, but it's kind of guided by the methods that we have to implement in this kind of a class. So this is event sourcing, and this one I'm really excited about because it gets really powerful. Now with event sourcing, often with event sourcing, you hear of CQRS, Command Query Responsibility Segregation. And what's happening with event sourcing is that the events are happening, they're getting persisted, and then after those events have been safely persisted, then you update views. So what I'm showing here in this diagram is that the views, I've got a couple of examples of these V-like icons that I've got here in the bottom. They represent views. Views also have APIs. They're just another service in this implementation. But what's happening is the data is being fed. As events are occurring, those events are being fed to these views so the views can update the view data. So I want to show you an example of that. So this is a class that needs to be implemented that handles the event. So what's happening here is that you can see there's like on item added method here, and you can see that what's passed into this class is the event and the state. The state here is, I really should probably call this a row because it's really the row in the view that's being passed here in the event. And what this method returns is that updated row. Now, again, what's happening here is the abstraction layer is retrieving that row from the view, if it exists. It's retrieving the event from the event journal, which is also, you can think of as a topic, because it's mechanically, it is a topic, basically. So all that's being handled by the abstraction layer, and it's just being fed into this code. So all we have to write as developers is, we got to update the row, and that's it. So with event, one thing that some developers, when they first see it, is like, oh man, I got to do a method for each of my events. It's like, yeah, sorry, there's no way around it. So I've got one for item added, item changed, item removed, checkout. But it's just kind of mechanical. It's pretty straightforward. But the point I was trying to make though is that there's this, it's like. I remember when dependency injection came out, and we were all so excited when Spring brought that out initially, and unleashed it on the Java world, and it was such a major thing. This is similar in that it's kind of state injection that's occurring here, an event injection. But it's like all the drudgery of say retrieving the event, retrieving the row from the database. All that time that we have to spend on that is kind of gone in this type of an implementation with this kind of abstraction. So these entities, they're services. Just like I said, they have an API. And they already come with kind of built-in gRPC and HTTP. And I'm showing you a particular implementation, but the point I'm trying to get across here is I think this is what we need to see in a lot of other implementations, not just what I'm talking about. And there are things like Dappers and Temporal and so on that are coming out that are doing very similar things. And I think this is really a great way to simplify our computing and allow us as developers to focus more on what we need to do, which is implement features. But also, this is say consuming from a topic. So say there's some Kafka topic or Google Pub Sub or Pulsar or something like that, where there's some external topic that comes into this application, and those things need to be processed. There's a third player here. First, I was talking about entities, and then I've talked about views. Well, there's a third component here. It's called an action, and an action is a stateless function. So in this case, an action is being fed messages by the abstraction layer. So the action isn't responsible for retrieving the messages from a topic. It's just being fed them as they come into the system. And then the action, what it's doing is it's transforming, say, the messages that are coming in from a topic into commands that are being passed into an entity. So the entity is kind of blissfully ignorant of who's sending it commands or who is using its output. All you're focused on when you're developing an entity is what, processing those commands and what state changes or events are being emitted. So it's a nice compartmentalization of the focus of concentration when you're building something. But this is where things get really fun. And I'm going to go into this in more detail in a bit. But it's where you start stringing together these entities into series of processing steps based on series of events, like cascading sequence of events. And I'll show you a couple real distinct examples of this coming up. But in this diagram, I'm showing, say, like there's the shopping cart entity on the left. Things are coming into it. It's sending out its events into some event journal, and the shopping cart's done. It doesn't care what's happening downstream. But in the event journal, what's plugged into it, in addition to a couple of views, is an action. And this action, in particular, in this case, is looking for checkouts. Because when a checkout occurs, that means we have an order, and we want to process that order. So there's a big difference between people loading up stuff in a shopping cart and abandoning it versus people when they hit the buy button and your system needs to react to it downstream. So this is a really cool way to kind of have that flow begin, right? And it's just by setting up an action that's consuming those events, looking for a checkout. When a checkout occurs, then this action is going to send a command to a order entity, basically saying, hey, we need to create an order and start processing that order. But also, like I said, this is there's lots of instances. So in this picture, that kind of going from this to this, I'm trying to show. Think of these entities as these durable, stateful objects, and there's multiple instances of them. And when the system's actually running, this is not a stateless system. This is a stateful system. So these entities exist somewhere in the cloud, somewhere in the cluster. But the abstraction layer is taking care of all the routing of commands to it, all the handling of persistence, all that's being handled, scaling up, scaling down, handling failures, all that kind of stuff. This is what these abstraction layers should do for us. And you can kind of think of it, it's also doing things that it's nice to know for us as developers, but it's really nothing we do about it. This is hot state, meaning that when an entity is pulled into memory from the persistence store because commands are being sent to it, it's the abstraction layer that will keep it in memory as long as it's needed, which means that it's going to do a form of caching so that as other commands come into the same entity, odds are very good that that entity is already in memory, and we don't have to make that round trip down to the database again to retrieve the state on every single command, which is inherent in the stateless systems. Which leads us back to this picture. So I've been talking about individual entities, and I'm kind of gave you a look at that line between the entities. But now, I'm just kind of playing with this term, but I was thinking about it was microstreams. And I was actually at another conference in London on Wednesday, and I was walking around the exhibition hall, and there's a company called microstreams.one. It's pretty cool. You might want to check it out. But I looked around to see who's been using the term microstreams when I was preparing this talk, and I didn't see too much with it, so I thought I'd go with it. So what do I mean by by microstreams? Well, it's something like this. So this is a demo application. It's in Java. You can take a look at it. It's in GitHub. The link is down below. It's in my user, McKee H3. It's just order processing Java demo. And it's all there. So what this thing does is it's an event-driven type of application. So on the left, there's a client interacting with their shopping carts. So they're adding information into their shopping carts. And so I'm kind of highlighting it here. That the shopping cart. When I highlight it, something's happened. And say that a particular shopping cart instance is checked out. So when that happens, it emits an event, which is picked up by the order entities, an order entity. Each arrow here, you can think of the arrowhead as an action. So the arrow, the shaft of the arrow, you can think of as a topic. The arrowhead is the action that's consuming the changes in that topic and then acting on them by sending, say, a command to the entity that it's pointed to. So an order gets created, and when an order is created, it emits an event which is picked up by two other entities. So one is order item, which is kind of just for a demonstration of kind of a reporting thing, which is okay. But the more interesting one is the shipping order. So an order is created, it emits an event, and a shipping order is created. Well, a shipping order is similar to an order, and this is just an example. It's not how I'm not saying this is the way it should work. Any of you that work on these e-commerce systems, kudos to you, because I know they're massively complicated, and this is a very simple example. But the shipping order kind of explodes out the order. And what I mean by that, say there's, the shipping order contains, like a list of order items. And say that, as an example, that an order has 2 items in it, one with a quantity of 1 and one with a quantity of 2. It blows it up so that there's sublists that contain items for each individual unit that needs to be shipped. So if you ordered a quantity of 2, there's going to be 2 additional levels of detail here. So in the shipping, shipping with 2 items, quantity 1, quantity 2, there's 3 of these stock items, I call them, or SKU items. So what happens when a shipping order is created, it emits an event that goes to what I call the order SKU item. So 3 order SKU items in that example I just mentioned would be created here. When these order SKU items are created, they each emit events. And there's a lot of concurrency happening here because it's all kind of happening at the same time now, which goes to stock, to a stock SKU item, as I called it. And what happens here gets a little bit more interesting. So I wanted to show you at a little bit, find a level of detail. So on the left is the order SKU item. It emitted that event to its journal. There's an action picking up those events. But the first thing the action does is it does a query against the view on the stock SKU items. And this query is, are there any available stock SKU items for that SKU? And their response comes back to the action, and it's decision time. If there is stock available, then what the action will do is send a command to a chosen stock SKU item and say, hey, I want to use you in this order, basically is what this command's saying. If there isn't sufficient stock, what the action will do is actually send a command back to the corresponding order SKU item and say, hey, there's no stock available right now, put yourself in a back order state. So this action in this example is doing, it's more than just trivially kind of transforming messages coming into commands. It's doing some processing here. What did I do? Oops, I hit too far, sorry. So the stock SKU item gets that command, and we go back to the diagram here. So this little arch here, that's what I'm showing here, that this action is querying a view, and that alters the command. So the stock SKU item gets a command, and again, I wish I had more time to go into it, but with CQRS, the responsibility is segregated, they're split. So views could be behind what's actually the current state of the data. So a view could say, yeah, this stock item's available, but it's the actual entities that know if they're available or not. So you have to take that in consideration when you're writing code. Anyways, the command goes into the stock SKU item and say the stock SKU item is available and everything's good. What the stock SKU item then is going to do, it emits an event, which is now picked up by the order SKU item. The order SKU item goes, great, I've been allocated some stock. Stock SKU items emit events that go back to the shipping order. So the shipping order is updating itself. As each unit of stock each unit in the order has been allocated a unit of stock, it's updating the order. And as the shipping order updates itself, it's letting the actual order object know, the order entity know that, how are things going with getting stock for this order. So this whole thing was this cascading sequence of events. The client hit the buy button, and the system kind of automatically flowed through, just event by event. And the thing is, I remember telling this to somebody, showing this internally at my company. I was, after I had got this thing working. And one guy came back and said, well, that looks kind of brittle. I said, no, it's absolutely not brittle, because the messaging here is event-driven, and it's at least once delivery. So everything will get delivered, which is very different from the RESTful synchronous types of messaging that we often do. This is highly resilient and highly concurrent as well. Now, the client, when it sent in that checkout request, the response went right back and said, yep, we got it. But it took a while. It's not instantaneous. It'll take some time, some milliseconds, for all this to flow all the way through and actually allocate all the stock to the order. But the customer doesn't care. All the customer cares about is, yep, but it's bought, and you said you're going to ship it to me. So that's this example. Here's another example that was based on kind of a proof of concept that we were doing with somebody. And so this example application, again, it's in GitHub. It's called Transactions Aggregator. It's in Java. It's under my user again, McKee H3. But in this case, this isn't the transaction topic is an external Kafka topic coming in from an external system, and the data here is merchant transaction data at very, very high volumes. Like the request was, can you handle like up, say, 20,000 messages per second? So really, really high volume for lots of big merchants. And so the design we came up with as a proof of concept was this one. And we're still experimenting with it, but it was a lot of fun. So the idea is that as messages are being pulled in from the topic, they create transaction entities. And when transaction entities are created, they emit events that are picked up by this thing I call the subsecond. And what a subsecond is a 10 millisecond window of time per merchant. So it's an entity that falls within a 10 millisecond time for a particular merchant. And then what it's doing is it's accumulating all the transactions that happen in that 10 millisecond window. And when one of these subsecond entities is activated, as I call it, it emits an event that tells its corresponding second, that this 10 millisecond window falls under. There's an entity for its corresponding second. Say, hey, we've got some transactions that need to be aggregated in your second. So the second's kind of keeping track of which 10 millisecond windows, which there could be up to 100, have transactions that need to be aggregated. When a second is activated, it does the same thing with a minute. So the minute, the second's telling its corresponding minute, hey, there's some transactions in this second that we need to aggregate. And it flows up to hours. So this is a big tree. The leaves are the transactions, and the branches all the way down to the trunk fall down through units of time. This is just kind of trying to keep activity, high activity, way up in the leaves, and have a quick way to kind of filter it down to much lower levels of activity through units of time. So it goes up to a day. So day says, all right, I got some transactions we need to aggregate, and it tells its corresponding merchant, all right, we got some data we need to aggregate. The merchant turns around and just emits an event that goes back to day and tells day, all right, harvest the data that you got right now, aggregate the data that you have right now. And the day goes back to its active hours go back to its active minutes, active seconds, gets back down to the subseconds. And while all this is going on, transactions are flowing in, thousands per second, right? They're just flowing into the system. So subseconds are getting created, seconds are getting created, all this activity is happening. But the merchant found out that, okay, I got some data in my day. Let me just tell the tree, harvest the data that you got right now. Because the goal of this system is to do periodic payments, say every 8 hours for a given merchant, or every day, or whatever the merchant wants. They want to do payments to these merchants. And the problem with this system was, well, you got this massive amount of data coming in, and it's like you can do a big batch operation when they want a payment and wait 15, 20, 30 an hour, or whatever it takes to process all that data. Or we could do something like this, because I'll show you what happens, but basically we'll give them a payment, like as soon as they want a payment, we'll give them what we got right now with no delay. So the sub-second gets this aggregation request. It goes through his list of unaggregated transactions, sums them all up, and then emits an event. Well, actually emits a bunch of events. It emits an event that goes back to its second with the summed value, but it also emits events that go back to its corresponding transactions to tell them which payment they were included and to kind of do the bookkeeping, which transactions have actually been included in a payment. And then the second gets that event, and once all of the sub-seconds, the active sub-seconds for a given second have reported in, then the second will sum up the data, the amounts that it has, and send it up to a minute. And then the minute waits until all of its active seconds sum up, and it just flows back up the tree. And it goes, and in this case, it just goes through a payment. So what's happening here, this was really cool because this is where I'm falling in love with eventing, because I implemented this system, we got it going, but we were still kind of thinking about, well, how do we trigger aggregations? And all of a sudden it occurred to me some days later that this could be implemented. Just as soon as the merchant sees that there's stuff to aggregate, go ahead and aggregate it. So there's this oscillation that occurs all day long. We're constant. The data's flowing in, and eventually this propagation of activation goes up to the merchant, which I initially showed you, and the merchant just goes back and says, "Harvest your data." It oscillates back and forth. Like it takes a few seconds for it to oscillate back and forth. But it's just constantly harvesting its data all throughout a payment period. So when they want to draw a payment, it's like, well, yeah, here's the amount. Here's what we have right now. Here's what we have so far. Take it. No delay. And then we go into, and that triggers a new payment cycle. And we just keep going. So it was like, when that thought occurred to me to add in this auto oscillation, this auto aggregation, and it was like so easy to do just through cascading events in this event-driven type of a flow, it freaked me out. It was like, man, this is too cool. So it's not just the end of the data ice age that is kind of starting to happen here. It's these kind of more frictionless abstraction layers. And we're kind of boldly starting to talk about it. It's database-less, it's broker-less, it's Kubernetes-less, it's ops-less, it's cloud services-less, it's, and of course it's serverless. I recently saw an article from somebody who'd been doing serverless for, I think, about 5 years, he said in the article. And he says, I'm out of the serverless cult. And it was a really great post, but a big part of the reason that he said he was out. Serverless on its own is great, and I think he was doing Lambdas, which are great, and Lambdas kind of started this whole serverless thing. But it was all the other services that they had to use to make things work that was driving them nuts. And that's what's kind of happening. In this whole age of DevOps, a lot of the responsibility for understanding how to do things falls to us as developers. And like I've been spending, before what I'm doing now, I spent the last couple of years doing things on Kubernetes. Love Kubernetes. It's a great leap forward, but it's like, oh man, YAML and this and that and all there's a lot, reading about it, learning about Kubernetes. I'm just spending all kinds of cycles on that. Same thing with other things like different flavors of databases, different flavors of message buses. Each one of these things, as we pick it up, we have to spend a lot of time, effort, and intellectual capacity on those things, which means all that time that you're spending on that stuff, you're not spending on, say, implementing core features of your applications and doing cool things like this. It's like here I was focused on the design. Just on the design, and then really kind of getting my head wrapped around eventing, and without all that other distractions, because I build this system, I deploy it, and it's running in a couple of minutes. And if something's wrong with my design, I go back and play around with it or fix it, whatever I have to do, and I can run unit tests and run it locally, but I can just deploy it to a production-ready environment, and it's ready to go. I mean, this is built to run on a serverless environment, and I don't want to go back to the other ways. I'm just spoiled rotten in doing these kind of things. So it's kind of these, I think that it's it's really time. Again, we're in the third decade of the 21st century. It's time that we insist on more of these types of powerful abstraction layers. So it's really this thing of abstracting away complexity and just increasing the simplicity. And this is what was hopefully, are we looking at the end of the data ice age and end of other, it's not the end of these technologies, it's the end of how we use these technologies is what I'm talking about. So I want to wrap up with just this one, I love this quote. And he's my favorite author, Arthur C. Clarke, but any sufficiently advanced technology is indistinguishable from magic. And what I mean by that is that over a long time, when I saw something new, in a lot of cases, sometimes I would look at it and go, oh, that's really cool, I want to learn about it. But too often, what I did was I would look at something and go, oh no, man, that's just, I don't get it, it's too different or something. It's magic. I'm not gonna bother with it. And I, over and over and over, and it took me way too long, but I finally started to realize I gotta quit doing that. I gotta start looking at these things because I gotta peel back the magic and understand. Because that's what I think we all love about our job is it looks like magic at first, but then we get a deep intuition about it, and that's the most fun. So. I think perhaps this looks like magic. Even event sourcing is kind of magic to some people, and I think it's just marvelous, event-driven event sourcing. So with that, I'm done. Thank you very much. What I was talking about is called Calyx. And Calyx, it's going to be officially out next week on the 17th. It's been out for a while. It was called Akka Serverless, but we rebranded it. So the whole rebranding effort's going public next week. And this is what I've been working on, and it got me so excited about these new abstraction layers. And take a look. I mean, it's free to try. It's really interesting. It's rocked my world as a developer. But like I said, there's Dapper, Temporal, and other things are coming out like it that are doing the same thing. So we're not the only ones, and I think we're going to see a lot more of this as time comes. So thank you. We have some time for questions. Okay. This is pretty cool. So if you abstract from persistence and act only on the inputs and return output effects, isn't that good old functional programming? Yeah. Yes, thank you. It is, right? It is. From the perspective, the entity you can think of as a pure function. And its only side effect, of course, is the return. So yes, it is very much like that. So what do I do? Oops. What if one of the layers will occur exception, and the data in the application are different in different databases? Well, and some sync message for vulnerability. Yeah. So I think the expectation is that problems in the abstraction layer are the problems of the people responsible for operating the abstraction layer. So in the case of Calyx, it's a platform as a service. I think like in Dapper, you do have more control of things. So you are responsible for databases and things like that. So you're going to see various implementations of this. And the other one was durability of the data, I think was basically the question. Yeah, for sure, the database, you can't expect that the database is going to be brittle, that the database has to be reliable, has to have failover capabilities, things like that. That's just an expectation of the abstraction layer. The next one, we had architecture like that and faced problems in terms of sync, transactions, sync UI updates, event journal state reconstruction, etc. It lacks simplicity. Yeah, I've seen this before. One of the more common questions is that things like schema migration. That one's a tough one. There's really no magic to that. By schema migration, it's like you design, say, a version of all your events for event sourcing, and then you want to massively revise that, and you want to revise the schema. So if it's forward compatible, that's good. You're lucky, and that shouldn't break anything. But say you want to do kind of a breaking thing, the only alternative I can think of is that you would stand up a new instance of a new entity that has the new schemas and let it sync up with the old instance. Let it consume all the data from the old instance and catch up. And once they catch up, make the new entity live and retire the old entity. But there's no real magic there. So there is complexity at that level, like in the question. There's no way around it. But I think the fact that the tools take on some of the responsibility, or the abstraction layer takes on some of the responsibility, it does simplify things, and it allows you to experiment more quickly with potential solutions. Is there a way to configure consistency requirements for CQRS example? For example, if you need to see changes introduced by your command immediately in your views. Yeah, that's a tough one, because with CQRS there is eventual consistency, typically. However, one of the things that we're thinking about, and I'm sure others will think about, are going to do something along these lines, is that right now we're using, they call it the write side and the read side. The write side is, let's say, your event journal, and the read side are your queryable views. And they're separate, they're physically separate. So one form of this that we're thinking about is that for some specific entities, non-event source entities, that we could make the state queryable. So that would mean that changes to the state there would be immediately viewable. But this is addressing the problem, like what I mentioned in the stock. When the order was trying to find stock that was available, it queried a view to look for available stock, and that view could be behind. So it could be that when the command is actually executed, that the stock is already gone. So you have to have compensating actions for that. So I've been dealing with that, and it's at least, I've only done a little bit, but in the stuff that I've done so far, the specific problems that I ran into where I had those kind of eventual consistency things to consider, it wasn't as bad as I thought it would be. Now, again, I know other people have done much more in this area, but it's like if you go into the design knowing that there's eventual consistency, then you just think about it, make it a fundamental part of your design. Is there any support for distributed transactions? No. That example I showed you, the stock and the order, is effectively two things that have to come to a mutually agreeable set of state changes. But it was done without a overlapping or overriding single transaction. It works, and I kind of like it. It doesn't all happen at once. And you have to think through the compensating actions, but then you kind of get into the whole saga type of thinking, which actually I think is kind of healthy in a way. I think maybe, don't hate me or hate me, but I think we've been hooked on acid too long. That acid transactions, atomic transactions, they come at a cost. Most of the performance problems I've run into in the applications that I've worked on for decades have always fallen on the database. And it's because the database is struggling to deal with concurrency. And it's kind of fun to look at systems where I'm solving the same problems, but where I don't have that bottleneck anymore. How to ensure that views are in sync when, well, these are great questions. Thank you so much. when when we query them. You can't. It's a feature. Think about that when you're implementing it. I know it's tough because we're so used to being hooked on acid, like I said. So, but I think in many cases it's not as bad as we might think. It's one of those things that's like you get used to it, and you kind of it gets into your rhythm of how you do design and how you do implementation. How do you validate data using view state, which can be stale and is eventually consistent? Yeah, that's a good one, because the decision, remember that the action did a query to see if there was available stock, and that query could be stale. It could be that new stock had been added to the system and the view doesn't know it yet. And that could happen. So I still really haven't dealt with that one, but that's one that I think we may have to deal with. There's a couple more, but we're out of time. So again, thank you so much for attending, and thank you so much for being here. I can kind of see you now. I'm getting used to the lights. There's people out there. I'm so happy. And if anybody wants to chat with me, I'd love to chat with you. I'll be around all day today. So thanks again.